Every moment, the moon is being pulled toward Earth. The same gravitational force that causes an apple to fall toward the ground is also acting on the moon, steadily drawing it inward across the vast space between our planet and its companion. And yet, the moon never plunges into Earth. Instead, it continues tracing its familiar path across the sky, night after night. At an average distance of about 384,400 kilometers, the moon moves sideways through space at nearly 3,680 kilometers per hour. That sideways motion changes everything. Rather than dropping straight toward Earth, the moon is constantly moving forward while gravity bends its path inward. The result is a curved trajectory that wraps around the planet. This is the quiet balance that creates an orbit. Gravity continually pulls the moon toward Earth, while the moon's sideways motion carries it across space at the same time. Because both motions happen together, the moon keeps falling, but the ground beneath it curves away just as quickly. In this exploration, we follow the physics behind that delicate motion, beginning with a question that has fascinated astronomers for centuries. Why is the moon always falling toward Earth, and yet never reaching it? Before we continue, if you feel comfortable doing so, a soft like or a quiet tap on subscribe would truly mean a great deal to me. Even a small gesture like that carries real encouragement. It reminds me that these calm explorations of the universe are reaching thoughtful listeners like you, and it helps this small corner of curiosity continue to grow. How can an object that is constantly falling toward Earth remain suspended above us for billions of years without ever touching the ground? This question appears simple at first glance, yet it quietly leads into one of the most fundamental ideas in celestial mechanics. The moon does not resist gravity. Earth pulls on it continuously. Every second, the moon accelerates toward our planet under the influence of gravity. And yet, the distance between Earth and the moon remains close to 384,000 kilometers on average. The explanation lies not in the absence of gravity, but in the presence of motion. When astronomers describe the moon's orbit, they are describing a situation in which two physical effects act together at the same time. Gravity pulls inward toward Earth, while the moon's sideways motion carries it forward through space. At the moon's current orbital distance, the balance between these two influences produces a continuous path around Earth rather than a direct fall toward the surface. Measurements show that the moon moves along its orbit at roughly 3,680 kilometers per hour relative to Earth. That sideways speed is not arbitrary. It is precisely the speed required for an object at that distance to remain in orbit around a planet with Earth's mass. If the moon traveled more slowly, gravity would gradually pull it inward and its orbit would shrink. If it traveled significantly faster, it could escape Earth's gravitational influence entirely. The idea that orbit represents a continuous fall first became clear during the 17th century. Before that time, the motion of celestial bodies was often explained through geometric descriptions without a physical mechanism connecting Earth and the heavens. The turning point came with the work of Isaac Newton. Newton recognized that the same force causing an apple to fall toward Earth also governs the motion of the moon. In 1687, he published Philosophiae Naturalis Principia Mathematica, where he proposed that gravitational attraction acts between all masses in the universe. According to Newton's analysis, the moon's motion can be understood by comparing two simultaneous movements. The first movement is the Moon's tendency to travel in a straight line through space due to its existing motion. The second movement is the constant inward acceleration caused by Earth's gravity. When these two effects combine, the Moon's path curves around Earth. Newton illustrated this concept through a thought experiment that has since become famous in physics. Imagine a cannon placed on a mountain high above Earth's atmosphere. If the cannon fires a projectile gently, the projectile travels forward for a short distance and then falls to the ground. If the cannon fires the projectile faster, it travels farther before falling. But if the projectile leaves the cannon with sufficient sideways speed, something remarkable occurs. As it falls toward Earth, the curvature of the planet causes the surface to drop away beneath it. The projectile continues falling but never reaches the ground. Instead, it circles the planet. In Newton's time, this idea was a theoretical insight. Centuries later, it became a practical reality. Artificial satellites launched during the 20th century operate according to exactly this principle. For example, satellites placed in low Earth orbit typically travel at speeds close to 7.8 kilometers per second. At that velocity, the spacecraft continuously falls toward Earth while moving forward fast enough to keep missing the surface. Astronauts aboard the International Space Station experience weightlessness because both the spacecraft and everything inside it are falling together along their orbital path. Gravity is still acting on them strongly. What changes is the relationship between motion and gravitational acceleration. Returning to the Moon, the same principle operates on a far larger scale. Earth's gravitational field reaches outward across space, decreasing gradually with distance. At the Moon's distance, the gravitational pull is weaker than at Earth's surface, yet still strong enough to bend the Moon's path. Careful measurements made through lunar laser ranging experiments provide precise data about the Moon's orbit. Reflectors placed on the lunar surface during the Apollo missions allow scientists to bounce laser pulses from Earth to the Moon and back again. By timing the return of these pulses, researchers measure the Earth-Moon distance with centimeter-level precision. These observations confirm that the Moon's motion follows the predictions of gravitational theory with remarkable accuracy. The Moon does not wander unpredictably. Its motion can be calculated years, decades, and even centuries into the future. Yet the orbit is not perfectly circular. The Moon follows an elliptical path in which its distance from Earth varies slightly during each cycle. At its closest point, known as perigee, the Moon approaches roughly 363,000 kilometers from Earth. At its farthest point, called apogee, the distance grows to around 405,000 kilometers. These variations influence the Moon's apparent size in the sky. When the Moon is near perigee, it appears slightly larger and brighter. When it is near apogee, it appears slightly smaller. Astronomers also recognize that the Earth-Moon system is not isolated from the rest of the solar system. The gravitational influence of the Sun subtly alters the Moon's orbit as well. This interaction produces gradual changes in the orientation and shape of the lunar orbit over long periods. Despite these complexities, the fundamental principle remains clear. The Moon's orbit is the result of gravity acting continuously on a body already moving sideways through space. Carl Sagan once emphasized how powerful this realization can be when he wrote, "The beauty of a living thing is not the atoms that go into it, but the way those atoms are put together." The same idea applies to orbital motion. Gravity alone would pull the moon inward. Motion alone would carry it away into S. This understanding reshapes how astronomers interpret motion across the universe. Planets remain in orbit around stars through the same balance. Binary stars circle one another through the same gravitational relationship. Even galaxies rotate because billions of stars move under the influence of shared gravitational fields. The Moon, therefore, offers a nearby example of a universal rule. What appears at first to be a stationary object in the sky is actually part of a dynamic gravitational system involving motion, energy, and distance. Yet another layer of investigation emerges when astronomers begin examining how this orbital balance evolves over time. The Moon's distance from Earth is not perfectly constant across geological history. Subtle physical processes within Earth's oceans slowly alter the energy of the Earth-Moon system. Those processes lead to a surprising discovery revealed through modern measurements. The Moon is not slowly approaching Earth as one might expect from a falling object. Instead, the Moon is gradually moving farther away, increasing its distance from Earth by a few centimeters each year, according to measurements from lunar laser ranging experiments conducted since the Apollo missions. In this exploration, we look more closely at the physical processes quietly reshaping the Earth-Moon system, beginning with a question that naturally emerges from those precise measurements. If gravity is constantly pulling the Moon toward Earth, why do modern observations show the Moon slowly drifting farther away instead of coming closer? If gravity never turns off, why has the Moon not already crashed into Earth? The force that pulls objects downward on our planet reaches far beyond the atmosphere, far beyond satellites, and continues across the entire distance, separating Earth from the Moon. Measurements of gravity show no sudden boundary where the force disappears. Earth attracts the Moon continuously, second after second, through empty space. Yet the Moon remains suspended in its orbit instead of collapsing inward. This apparent contradiction became one of the most important clues in the history of physics, and resolving it required a deeper understanding of motion than humanity had ever developed before. The explanation begins with a careful look at how motion behaves when gravity acts sideways rather than directly downward. Every object that moves through space carries momentum, which simply means that motion tends to continue unless something changes it. If a spacecraft is launched into orbit around Earth, its engines fire only briefly. After that moment, the engines stop completely. From that point forward, the spacecraft continues moving because of its existing motion, while gravity gently bends the path inward. The Moon follows exactly the same principle. Astronomers studying the Moon's motion have measured its orbital speed with great precision. At its average distance of about 384,400 kilometers from Earth, the Moon moves sideways through space at roughly 1 kilometer per second. That motion means the Moon travels around 2,400 kilometers every 40 minutes. During that same time, interval gravity pulls the Moon slightly inward toward Earth. The key detail is how small that inward drop actually is. If one calculates the amount of downward curvature in the Moon's orbit over a single second, the path bends inward by only about 1 millimeter. That tiny curvature accumulates gradually, producing the smooth circular path we recognize as an orbit. This idea was first understood clearly in the 17th century through the work of Isaac Newton. Newton recognized that gravity does not simply pull objects downward, it also alters the direction of motion. Instead of bringing the moon straight toward Earth, gravity continuously redirects the moon's forward movement, creating a curved trajectory. The historical story behind this realization is often connected to Newton's reflections while studying falling objects and planetary motion. At the time, astronomers already knew that the moon completed one orbit roughly every 27 days. They also knew the moon remained at a nearly constant distance from Earth. Newton asked a simple but powerful question. If the moon is constantly being pulled toward Earth, how far does it fall during each second of its motion? By comparing the strength of gravity at Earth's surface with the distance of the moon, Newton realized that the moon should fall inward at a very slow rate consistent with the curvature of its orbit. This result provided strong evidence that gravity follows a pattern in which the force becomes weaker as distance increases. Today, this relationship is described mathematically as the inverse square law, but the underlying meaning can be understood without equations. When distance doubles, gravitational attraction becomes 4 times weaker. When distance increases threefold, the attraction becomes 9 times weaker. Because the moon is so far from Earth compared with objects on the ground, the gravitational pull is much weaker than the gravity we feel beneath our feet. Even so, it remains strong enough to curve the moon's path. Modern observations confirm this interpretation with extraordinary accuracy. Laser ranging experiments performed by scientists at the National Aeronautics and Space Administration use mirrors placed on the lunar surface during the Apollo missions. By sending pulses of laser light to these mirrors and measuring the travel time of the reflected signal, researchers determine the Earth-Moon distance with precision measured in centimeters. These experiments show that the moon's orbit behaves exactly as predicted by gravitational theory. The path curves gently inward at every moment, but the moon's forward motion carries it beyond the reach of direct impact. In effect, the moon keeps missing Earth. This principle applies to every orbiting body in the universe. Artificial satellites around Earth remain aloft, not because gravity disappears, but because their sideways velocity continually carries them beyond the point where gravity would bring them down. The same mechanism governs the motion of planets around the Sun. Consider Earth itself. Our planet travels around the Sun at an average speed of about 30 kilometers per second. Solar gravity continuously pulls Earth inward, but Earth's forward motion prevents collapse into the Sun. Instead, the result is a stable orbit that has persisted for billions of years. This balance between gravity and motion is sometimes described as a state of perpetual falling. The phrase captures an important physical idea. Objects in orbit are constantly accelerating inward under the influence of gravity. But because their sideways velocity remains large, they keep missing the surface they are falling toward. Astronauts aboard the International Space Station experience this phenomenon directly. The station orbits Earth at an altitude of roughly 400 kilometers, while moving at nearly 28,000 kilometers per hour. Both the station and the astronauts inside it are falling toward Earth continuously. Because everything inside the station falls at the same rate, astronauts experience the sensation of weightlessness. The moon's orbit is essentially the same physical situation, extended across a much larger distance. Instead of circling Earth every 90 minutes like the space station, the moon requires about 27 days to complete a full revolution relative to distant stars. Yet the mechanism that keeps it aloft is identical. Evidence for this interpretation continues to accumulate through modern space missions. Lunar orbiters, operated by the National Aeronautics and Space Administration and the European Space Agency, track subtle variations in the Moon's gravitational environment. These measurements allow scientists to reconstruct the internal structure of the Moon and refine models of orbital dynamics. One particularly revealing mission was the Gravity Recovery and Interior Laboratory mission, launched in 2011. 2 spacecraft orbited the Moon in tandem, while measuring tiny variations in gravitational pull caused by differences in lunar mass distribution. The resulting data allowed scientists to map the Moon's internal structure with unprecedented accuracy. The findings confirmed that gravitational interactions shape every aspect of the Earth-Moon system. Slight irregularities in the Moon's gravity influence spacecraft trajectories. Earth's gravity influences the Moon's orbital path. The Sun's gravity adds an additional layer of complexity by gently perturbing the orbit over time. Despite these complications, the fundamental explanation remains elegantly simple. The Moon does not crash into Earth because it possesses enough sideways velocity to continually bypass the planet while gravity bends its path inward. Carl Sagan once summarized the importance of understanding motion and gravity with a statement that reflects the spirit of scientific exploration. He wrote, "We are a way for the cosmos to know itself." The motion of the Moon offers one of the clearest examples of that principle in action. By studying the trajectory of a familiar object in our sky, scientists uncovered laws that govern motion across the entire universe. The Moon therefore remains suspended, not because gravity fails to reach it, but because gravity and motion interact in a precise and predictable way. Every hour, the Moon falls slightly toward Earth. Every hour, its forward motion carries it beyond the point where impact would occur. The result is an elegant pattern of motion that has persisted for more than 4 billion years. Yet this explanation introduces another layer of curiosity that continues to draw attention once the mechanics of falling become clear. The history of physics reveals that Isaac Newton once explored this same puzzle through an unusual mental experiment involving artillery fired from a mountaintop. Did Isaac Newton solve the Moon's mystery with an imaginary cannon? What if the secret behind the Moon's motion was hidden inside a simple thought experiment involving a cannon on top of a mountain? The image may sound almost playful at first glance, yet within that imagined scene lies one of the most powerful explanations ever proposed for how objects move in space. By thinking carefully about what would happen if a cannonball were fired faster and faster across Earth's surface, Isaac Newton uncovered the physical principle that allows the Moon to circle Earth without crashing into it. The context for this idea reaches back to the 17th century, when astronomers were still trying to reconcile 2 different traditions of understanding the heavens. Observational astronomy had already advanced greatly through the work of figures such as Nicolaus Copernicus, Johannes Kepler, and Galileo Galilei. Their observations showed that planets moved around the Sun and followed predictable paths through space. But the deeper cause behind those motions remained unclear. Johannes Kepler had already described 3 laws governing planetary motion earlier in the century. His work revealed that planets travel in elliptical paths and move faster when they approach the Sun. These patterns described how motion behaved, yet they did not explain why such motion occurred. Isaac Newton approached the problem from a different direction. Rather than focusing first on planets, he began by studying the motion of objects near Earth. Through experiments and calculations, he recognized that motion follows simple principles. Objects continue moving unless a force alters their path. When a force acts continuously, motion curves instead of remaining straight. At some point during his reflections, Newton imagined an unusual scenario. Suppose a powerful cannon were placed on a very high mountain, tall enough that air resistance could be ignored. If the cannon fired a projectile horizontally, the ball would travel forward while gravity pulled it downward. At low speed, the ball would arc through the air and eventually strike the ground some distance away. Increasing the speed would carry the ball farther before gravity brought it down. If the speed became extremely large, something remarkable would occur. Because Earth's surface curves away beneath the projectile, the ground would drop slightly during the ball's flight. If the cannonball moved forward fast enough, the curvature of Earth would match the downward fall of the projectile. In that situation, the ball would never reach the ground at all. Instead, it would continue circling Earth along a curved path. In modern terms, the cannonball would become a satellite. This imagined experiment appears in Newton's book Philosophiae Naturalis Principia Mathematica, published in 1687. The diagram in that work shows a cannon positioned atop a mountain with several curved trajectories drawn outward. Each path corresponds to a different firing speed. The slowest trajectory falls back to Earth quickly. A faster shot travels farther before returning. A still faster projectile completes a full circuit around Earth. In that final case, the cannonball never lands. It becomes an orbiting body. This insight transformed astronomy because it linked motion on Earth with motion in the heavens. The same physics that governs a falling stone also governs the moon. The moon is essentially performing the same motion as Newton's imagined cannonball, except its sideways speed and distance allow it to remain in orbit indefinitely. Today, we can test this idea using real measurements of the moon's motion. Observations show that the moon travels through space at roughly 1 kilometer every second along its orbital path. Meanwhile, gravity pulls the moon inward toward Earth with a small but steady acceleration. If Earth suddenly disappeared, the moon would continue traveling through space in a straight line, according to the laws of motion. Because Earth remains present, its gravity continually bends the moon's trajectory. The curved path that results from this balance is exactly what Newton's thought experiment predicted centuries ago. Modern spacecraft navigation provides direct confirmation of this principle. When engineers send probes toward the moon, they calculate the spacecraft's trajectory using the same gravitational laws Newton discovered. The spacecraft initially travels along a curved path determined by Earth's gravity. As it approaches the moon, lunar gravity gradually reshapes the trajectory again. One example is the Lunar Reconnaissance Orbiter launched by the National Aeronautics and Space Administration in 2009. This spacecraft entered lunar orbit by adjusting its velocity carefully so that the moon's gravity would capture it into a stable path. The maneuver relied entirely on gravitational physics first described in Newton's work. Another example comes from missions studying the moon's gravitational field. The Gravity Recovery and Interior Laboratory mission, launched by the National Aeronautics and Space Administration in 2011, used 2 spacecraft flying in formation around the moon. By measuring tiny changes in the distance between the 2 probes, scientists mapped variations in lunar gravity. These measurements revealed how mass is distributed inside the Moon and helped refine models of its internal structure. Yet the fundamental motion of those spacecraft remained governed by the same balance between forward velocity and gravitational attraction described in Newton's Cannon thought experiment. Astronomers studying planetary motion often refer to this balance as orbital mechanics. The concept is simple at its core. A body moving sideways through space continues forward while gravity curves its path inward. If the speed is too slow, the body falls directly toward the central object. If the speed is too high, it escapes entirely. Between those extremes lies a stable orbit. This principle applies not only to moons and satellites, but to entire planetary systems. Earth orbits the Sun using exactly the same balance between motion and gravitational attraction. The Sun's gravity continually bends Earth's path inward, while Earth's forward motion prevents collapse. Carl Sagan once described the power of such discoveries in a way that captures the spirit of scientific exploration. He wrote, "Extraordinary claims require extraordinary evidence." Newton's explanation of orbital motion earned acceptance precisely because its predictions matched observations with remarkable accuracy. From the motion of planets to the trajectories of spacecraft, the same laws continue to describe reality today. The Moon's orbit, therefore, represents more than a familiar sight in the night sky. It stands as a continuous demonstration of Newton's insight. Every second, the Moon moves forward through space while gravity pulls it inward. The result is a path that curves endlessly around Earth. This understanding also reveals something subtler about the Earth-Moon system. The Moon does not orbit a perfectly fixed Earth. Both bodies influence each other through gravity, producing motion that is slightly more complex than Newton's original Cannon diagram might suggest. That detail leads into the next stage of the exploration, where the motion of the Earth-Moon system reveals that neither body sits completely still while the other circles around it. The deeper mechanics behind that relationship appear in the question: is the Moon really orbiting Earth, or are both of them circling something hidden? What if the Moon is not truly circling Earth in the simple way most diagrams suggest? The familiar picture found in textbooks often shows Earth standing still while the Moon travels around it in a smooth loop. That picture is convenient, easy to draw, and helpful for early explanations. Yet when astronomers measure the motion of the Earth-Moon system with high precision, they discover something more subtle. Earth is not standing still at all. The Moon is not the only body in motion. Both objects are moving together around a point in space that is not located exactly at the center of Earth. This point is known in physics as the center of mass of the system. Astronomers often call it the barycenter. It is the position where the combined mass of two bodies balances perfectly. If two objects are connected by gravity, neither one truly circles the other alone. Instead, both bodies orbit around this shared point. In the Earth-Moon system, the barycenter lies inside Earth, but not at its center. Careful calculations using the masses of both bodies show that this balance point sits roughly 4,670 kilometers away from Earth's center. That location places it about 1,700 kilometers beneath Earth's surface. This means Earth itself performs a small circular motion while the Moon travels along its larger orbit. From a distance, the two bodies appear to dance around an invisible pivot point between them. To understand why this happens, astronomers begin with the basic concept of gravitational interaction. Gravity does not act in only one direction. Whenever two masses attract each other, each object pulls on the other simultaneously. The Moon pulls on Earth, just as Earth pulls on the Moon. The difference lies in the enormous disparity between their masses. Earth contains about 81 times more mass than the Moon. Because Earth is far heavier, its motion around the barycenter is much smaller than the Moon's. Nevertheless, the motion exists. Earth slowly shifts position as the Moon travels through its orbit. Over the course of each lunar month, Earth traces a subtle circular path around the barycenter, while the Moon follows its larger trajectory. Astronomers can detect this movement using extremely precise measurements of Earth's position in space. Modern tracking systems monitor the location of Earth relative to distant quasars, whose positions remain effectively fixed across cosmic distances. These measurements reveal that Earth wobbles slightly as the Moon orbits. The existence of this shared center of mass also explains certain features of lunar motion that puzzled early observers. For example, the Moon's orbit does not appear perfectly centered on Earth when plotted using high-precision data. Instead, the orbital path reflects the combined motion of both bodies around the barycenter. Space missions have confirmed this picture repeatedly. Spacecraft navigating through the Earth-Moon system must account for the barycenter when calculating trajectories. Even small deviations in gravitational modeling would lead to navigation errors over long distances. One of the clearest confirmations comes from laser ranging experiments that measure the Earth-Moon distance with centimeter accuracy. Reflectors placed on the lunar surface during the Apollo missions allow scientists to track the Moon's exact position relative to Earth. The resulting data show that the Earth-Moon pair moves together around their shared center of mass. The concept of a barycenter extends far beyond our planet and its satellite. In fact, every pair of gravitationally bound objects in the universe behaves in this way. Binary star systems provide a striking example. In many regions of the Milky Way, astronomers observe two stars orbiting each other around a common barycenter. Sometimes the masses of the stars are nearly equal, which places the barycenter in the empty space between them. In such systems, both stars trace large, symmetrical orbits. In other binary systems, one star is far more massive than the other. In those cases, the barycenter lies inside the larger star, and the smaller star appears to orbit it. Yet the larger star still moves slightly in response to the gravitational pull of its companion. This same principle has become an essential tool for discovering planets around distant stars. When a planet orbits a star, the star itself performs a small wobble around the barycenter of the system. Astronomers can detect this wobble by measuring subtle shifts in the star's spectrum. Using this technique, known as the radial velocity method, scientists have discovered hundreds of planets orbiting distant suns. The first confirmed detection of this type occurred in 1995, when astronomers Michel Mayor and Didier Queloz identified a planet orbiting the star 51 Pegasi. The discovery relied on detecting the tiny motion of the star caused by its unseen companion. In our own solar system, the Earth-Moon barycenter plays an important role in understanding the dynamics of planetary motion. As the Moon orbits Earth, the barycenter itself follows a path around the Sun. The entire Earth-Moon pair, therefore, travels together through space as a gravitational unit. This detail becomes important when calculating spacecraft trajectories leaving Earth for other destinations. Engineers planning missions to Mars or the outer planets must account for the exact motion of the Earth-Moon system relative to the Sun. Ignoring the barycenter would introduce small but significant errors over millions of kilometers. Observations from space agencies such as the National Aeronautics and Space Administration and the European Space Agency continue to refine our understanding of these gravitational interactions. Data from lunar orbiters and deep space tracking networks provide increasingly accurate measurements of the Earth-Moon system's motion. Carl Sagan once reflected on the power of such discoveries when describing humanity's attempt to understand the universe. He wrote, "Somewhere, something incredible is waiting to be known." The discovery that Earth itself moves around a hidden pivot point with the Moon illustrates how deeper investigation often reveals layers of motion invisible at first glance. When people look up at the Moon, the scene appears simple. A bright disk travels slowly across the night sky while Earth seems solid and unmoving beneath our feet. Yet the physical reality involves two worlds locked in mutual motion around a point hidden deep within Earth's interior. That shared motion continues every moment. Earth shifts slightly as the Moon advances along its orbit. The Moon curves along its path, while Earth responds in return. Together, they trace a gravitational partnership that has persisted for billions of years. Yet even this elegant picture raises another layer of investigation. If gravity alone maintains this delicate motion between Earth and the Moon, why does the system require no engines, no propulsion, and no constant correction to keep the orbit stable? Why does the Moon remain suspended in orbit for billions of years without engines, without fuel, and without any visible mechanism maintaining its motion? Every spacecraft launched from Earth requires propulsion, navigation corrections, and careful monitoring. Yet the Moon continues circling our planet in stable motion without any intervention. Understanding why this happens reveals one of the most precise balances in celestial mechanics, where momentum and gravity interact continuously without interruption. The Moon completes one full orbit around Earth relative to distant stars in about 27.3 days. During that time, it travels along a path roughly 2,400,000 kilometers long. Its average orbital speed is close to 1 kilometer per second. At every moment along that path, Earth's gravity pulls the Moon inward, while the Moon's forward motion carries it sideways through space. This interaction between gravity and momentum is the central reason the Moon does not require propulsion. When a spacecraft leaves Earth, engines accelerate it to a specific speed that matches the gravitational environment it enters. Once that speed is reached, the engines can shut down. The spacecraft continues moving because motion in space does not fade away unless a force acts to slow it down. The Moon acquired its orbital motion during the earliest stages of the Earth-Moon system. Geological and dynamical evidence indicates that the Moon formed approximately 4,500,000,000 years ago after a large collision between the young Earth and a planetary body roughly the size of Mars. This event, known as the Giant Impact Scenario, produced a disk of debris orbiting Earth. Over time, that material gradually assembled into the Moon. The fragments orbiting Earth already possessed substantial angular momentum from the impact. As the debris gathered into a single body, that motion became the orbital velocity that still carries the Moon through space today. The idea that motion persists without continuous force became clear through the work of Isaac Newton in the 17th century. Newton recognized that objects in motion remain in motion unless acted upon by another force. Gravity then modifies the direction of motion rather than eliminating it. In the case of the Moon, Earth's gravity continually curves the Moon's trajectory. Instead of pulling the Moon directly inward, gravity redirects its path so that it circles Earth. The Moon therefore remains in a state of continuous freefall while moving forward at high speed. This balance between gravitational attraction and forward motion allows the orbit to remain stable for extremely long periods. In practice, the orbit changes slightly over time because additional forces are present in the solar system. The gravitational influence of the Sun, the distribution of mass inside Earth and the Moon, and tidal interactions all contribute subtle adjustments to the orbit. Despite these influences, the fundamental mechanism does not require active correction. The Moon's momentum and Earth's gravity maintain the orbit naturally. One of the most striking consequences of this long-term interaction is the phenomenon known as tidal locking. Observers on Earth always see the same hemisphere of the Moon. The far side remained completely unseen by human eyes until spacecraft photographed it during the 20th century. The explanation involves the gravitational effect that Earth exerts on the Moon's internal structure. Early in the Moon's history, its rotation was faster than it is today. Gravitational tides raised slight bulges in the Moon's solid body, stretching the shape of the Moon along the line connecting it to Earth. Because the Moon was not perfectly rigid, these bulges experienced friction inside the lunar interior. Over millions of years, this friction converted rotational energy into heat. As energy dissipated, the Moon's rotation gradually slowed. Eventually, the rotation period matched the orbital period. At that point, the same side of the Moon remained facing Earth at all times. This configuration is dynamically stable because the tidal bulge now points directly toward Earth. The evidence for tidal locking appears clearly in lunar observations. Astronomers studying the Moon's rotation and orbit find that both cycles take about 27.3 days relative to distant stars. Because the motions are synchronized, the same hemisphere always remains visible. Spacecraft observations have revealed the differences between the near side and far side of the Moon. The near side contains large dark plains formed by ancient volcanic activity. The far side, photographed first by the Soviet spacecraft Lunar 3 in 1959, is dominated by heavily cratered highlands. Modern missions continue exploring these differences. The Lunar Reconnaissance Orbiter, operated by the National Aeronautics and Space Administration, has mapped the Moon's surface in extraordinary detail since its arrival in lunar orbit in 2009. Data from this mission have helped scientists study the geological evolution of both hemispheres. The stability of the Moon's orbit also allows precise measurement techniques that support modern astronomy. During the Apollo missions between 1969 and 1972, astronauts placed reflective panels on the lunar surface. Scientists now send laser pulses from Earth to these reflectors and measure how long the light takes to return. Because light travels at a known speed, the round-trip travel time reveals the Earth-Moon distance with remarkable precision. These experiments show that the Moon's orbit behaves exactly as predicted by gravitational theory. They also reveal a subtle long-term change in the orbit. The Moon is slowly moving away from Earth at a rate of about 3.8 centimeters per year. This motion results from tidal interactions between Earth's oceans and the Moon's gravitational field. When ocean tides move across Earth's surface, friction transfers a small amount of rotational energy from Earth to the Moon's orbit. As a result, Earth's rotation gradually slows, while the Moon's orbital distance increases slightly. Even with this gradual outward drift, the essential balance between gravity and momentum remains intact. The Moon does not require engines or propulsion because the forces acting on it already produce the correct motion. Carl Sagan once described the elegance of physical laws in a line that captures the spirit of scientific discovery. He wrote, "The beauty of a living thing is not the atoms that go into it, but the way those atoms are put together." In celestial mechanics, the same idea appears in a different form. The stability of an orbit emerges not from a hidden mechanism but from the precise arrangement of motion and gravity. Every second, the Moon moves forward through space while gravity curves its path toward Earth. No thrust is required, no external support exists, and no adjustment is necessary for the orbit to continue. Yet this long-term stability depends on a delicate balance. If the Moon's speed were significantly different from its current value, the orbit would change dramatically. A slower motion would allow gravity to pull the Moon into a tighter orbit. A faster motion could allow the Moon to escape Earth entirely. This sensitivity raises a deeper curiosity about the relationship between velocity, distance, and gravity in orbital motion. Understanding how small changes in speed might alter the Moon's path. Could the Moon ever fall for real if its speed changed by just a little? How stable is the Moon's path around Earth if the balance between gravity and motion were disturbed even slightly? The calm appearance of the Moon crossing the night sky suggests permanence, yet the mechanics behind its orbit depend on a very specific relationship between distance, velocity, and gravitational attraction. The Moon remains in orbit not because space holds it in place, but because its motion has exactly the speed required for Earth's gravity to curve its path without pulling it directly inward. Understanding how sensitive this balance can be reveals why the Moon's orbit works so reliably, and what might happen if that motion were different. The Moon travels around Earth at an average speed of about 1,000 meters every second. At its average orbital distance of roughly 394,400 kilometers, this velocity produces a curved path that repeats every 27.3 days relative to distant stars. Earth's gravity constantly pulls the Moon inward, while the Moon's sideways motion prevents it from descending directly toward the planet. The stability of this arrangement depends on the relationship between gravitational pull and forward motion. If the Moon were moving significantly slower along its orbit, gravity would bend its path more sharply inward. Over time, the orbit would shrink, bringing the Moon gradually closer to Earth. In the extreme case where the Moon lost most of its orbital velocity, the curved trajectory would collapse entirely. The Moon would begin falling directly toward Earth in a long descending arc. The time required for such a fall would depend on the starting distance and the gravitational acceleration acting along the path. Astronomers can estimate this scenario using the known gravitational strength at the Moon's orbital distance. At that location, Earth's gravitational acceleration is about 0.0027 meters per second squared. Over time, this acceleration would gradually increase the Moon's inward speed as it approached Earth. The result would not resemble the slow motion of the current orbit. Instead, the Moon would accelerate continuously as it descended. The gravitational attraction would grow stronger as the distance decreased, producing an increasingly rapid fall. Fortunately, the Moon's actual velocity lies within the range that allows a stable orbit. In fact, the value of that velocity corresponds closely to what physicists call orbital speed. Orbital speed represents the precise sideways motion required for an object to remain in continuous free fall around a central body. If the Moon were moving slightly faster instead of slower, a different outcome would occur. A greater sideways velocity would reduce the curvature of the orbit. Instead of circling Earth along its current path, the Moon would drift outward into a larger orbit. If the velocity increased beyond a certain threshold, the Moon could escape Earth's gravitational influence entirely. This threshold is often described as escape velocity. At the Moon's orbital distance, the escape speed relative to Earth is a little more than 1.4 kilometers per second. That value represents the speed required for an object to move away from Earth indefinitely without falling back. Because the Moon's actual orbital speed is lower than that limit, Earth's gravity continues to guide its motion. This balance between speed and gravitational pull appears in every orbiting system in the universe. Planets circle stars under the same principle. Artificial satellites remain around Earth because their velocity lies within the range required for orbital motion. Space missions offer clear demonstrations of this sensitivity. When engineers send spacecraft toward the Moon, they must calculate the velocity of the spacecraft with extraordinary precision. A small difference in speed can determine whether the spacecraft enters orbit, passes by the Moon, or returns toward Earth. One example occurred during the Apollo missions conducted by the National Aeronautics and Space Administration between 1969 and 1972. The spacecraft traveling from Earth to the Moon followed a trajectory carefully designed to intersect the Moon's gravitational field at the correct velocity. Once near the Moon, the spacecraft fired its engine briefly to reduce speed and allow lunar gravity to capture it into orbit. Without that carefully timed adjustment, the spacecraft would not have remained around the Moon. If its speed were slightly higher, it would have continued past the Moon and escaped back into solar orbit. If the speed were lower, it could have descended toward the lunar surface. The Moon itself required no engines to reach its present orbit, because its velocity originated during the earliest stages of the Earth-Moon system. The giant impact event that formed the Moon generated enormous amounts of angular momentum. As debris coalesced into the Moon, that motion naturally produced an orbital trajectory. Over billions of years, the orbit has remained remarkably stable. Small changes occur through gravitational interactions with Earth and the Sun. These effects produce subtle variations in orbital distance and orientation, but they do not disrupt the overall balance. Measurements obtained through lunar laser ranging experiments confirm that the Moon's orbit behaves precisely as predicted by gravitational physics. Reflectors placed on the lunar surface during the Apollo missions allow scientists to measure the Earth-Moon distance with accuracy measured in centimeters. These observations reveal that the Moon slowly moves away from Earth at a rate of about 3.8 centimeters per year. This gradual outward motion occurs because tidal interactions transfer rotational energy from Earth to the Moon's orbit. Ocean tides, raised by the Moon, create friction that slightly slows Earth's rotation. Some of that lost rotational energy moves into the Moon's orbital motion, increasing its distance from Earth. Even though this effect changes the orbit slowly, it does not threaten the Moon's stability. The change is extremely gradual compared with the timescale of the Moon's orbital period. At the present rate, the Moon would require billions of years to reach a significantly different distance. Carl Sagan once reflected on the predictability of natural laws with a line that captures the reliability of physical processes. He wrote, "Nature is always more subtle, more intricate, more elegant than what we are able to imagine." The orbit of the Moon illustrates that idea with remarkable clarity. A delicate balance between velocity and gravity produces a motion that remains stable across immense spans of time. Every second, the Moon moves forward through space, while Earth's gravity curves its path inward. The resulting orbit persists because the speed of the Moon lies within a narrow range that maintains this balance. Yet the motion we observe today did not remain unchanged throughout the history of the Earth-Moon system. Geological evidence and laser ranging experiments reveal that the Moon has slowly migrated outward over billions of years. Why is the Moon quietly escaping instead of coming closer? What if the Moon is not slowly falling toward Earth at all, but gradually moving away from it year after year? The familiar image of gravity pulling objects inward suggests that satellites should spiral closer over time. Yet precise measurements reveal the opposite pattern. The Moon is increasing its distance from Earth by about 3.8 centimeters every year. This discovery did not come from speculation or theory alone. It emerged from one of the most precise experiments ever performed between two celestial bodies. The key evidence comes from devices placed on the Moon during the Apollo missions of the late 1960s and early 1970s. Astronauts from the National Aeronautics and Space Administration carried with them specialized instruments known as retroreflectors. These panels contain arrays of carefully aligned mirrors designed to reflect incoming light directly back toward its source. After the astronauts installed these reflectors on the lunar surface, scientists on Earth began performing an experiment that continues today. Powerful lasers are fired from observatories toward the Moon. A tiny fraction of the laser light reaches the reflectors and returns to Earth. By measuring the travel time of the returning light pulse, astronomers determine the exact distance between Earth and the Moon. Because light travels at a known speed of about 300,000 kilometers per second, the time required for the round trip provides an extremely precise measurement. The total travel time of the laser pulse is roughly 2.5 seconds. Within that brief interval, the light covers a distance of nearly 800,000 kilometers as it travels to the Moon and back. Modern instruments can measure the timing of this journey with precision better than a billionth of a second. This extraordinary accuracy allows scientists to detect extremely small changes in the Moon's orbit. Over decades of observations, a consistent trend has appeared. The average distance between Earth and the Moon is slowly increasing. This gradual outward movement is known as lunar recession. The process is not caused by a mysterious force pushing the Moon away. Instead, it arises from the exchange of energy between Earth's rotation and the Moon's orbit. To understand the mechanism, it helps to consider how tides operate on Earth. The gravitational pull of the Moon raises two tidal bulges in Earth's oceans. One bulge faces the Moon directly, while another forms on the opposite side of the planet. If Earth were covered entirely by water and rotated very slowly, these bulges would line up exactly with the Moon. In reality, Earth rotates once every 24 hours, far faster than the Moon completes an orbit. Because of this difference in timing, the tidal bulges are carried slightly ahead of the Earth-Moon line by Earth's rotation. This small shift produces an important effect. The mass of the ocean bulges exerts a gravitational pull on the Moon. Because the bulges lie slightly ahead of the Moon's position, the pull includes a forward component along the Moon's orbit. That forward tug transfers a tiny amount of energy from Earth's rotation into the Moon's orbital motion. As a result, the Moon gains orbital energy and moves into a slightly larger orbit. At the same time, Earth loses rotational energy and its spin gradually slows. This process can be measured directly through astronomical observations. Historical records of eclipses dating back thousands of years show that Earth's rotation is gradually slowing by a few milliseconds per century. The slowing corresponds precisely with the increase in the Moon's orbital distance. In this way, the Earth-Moon system behaves like a pair of interacting gears exchanging energy through gravitational tides. The rotation of Earth powers the gradual expansion of the Moon's orbit. The existence of this mechanism was first proposed in the 19th century when scientists began studying tidal friction in detail. Later observations confirmed that the transfer of angular momentum between Earth and the Moon explains the observed recession rate. Modern measurements from lunar laser ranging experiments provide some of the strongest evidence supporting this explanation. Observatories in the United States and Europe continue to fire laser pulses toward the Apollo reflectors, recording the distance with increasing accuracy. Data from these experiments match the predictions of tidal theory remarkably well. The recession of the Moon also offers a glimpse into the early history of the Earth-Moon system. When the Moon first formed roughly 4,500 million years ago, it likely orbited much closer to Earth. Geological evidence suggests that the early orbital distance may have been less than 100,000 kilometers. At that time, tidal forces between the two bodies were far stronger than they are today. These powerful interactions rapidly transferred rotational energy from Earth to the Moon's orbit. Over millions of years, the Moon migrated outward to its present distance of approximately 384,000 kilometers. Evidence for this ancient evolution appears in tidal deposits preserved in sedimentary rock formations. Certain geological layers contain patterns created by ancient tides, allowing scientists to estimate the length of Earth's day hundreds of millions of years ago. These records show that Earth once rotated much faster than it does today. Carl Sagan once described the significance of studying such processes with a statement that captures the essence of scientific curiosity. He wrote, "Understanding is a kind of ecstasy." The slow outward motion of the Moon illustrates how subtle physical processes can reshape planetary systems over immense spans of time. Although the Moon is drifting away from Earth today, the process unfolds extremely slowly. At the current rate of 3.8 centimeters per year, the Moon would move only about 38 meters farther away in 1,000 years. Even over millions of years, the change remains gradual compared with the enormous distance already separating the two bodies. Yet this steady outward migration reveals that the Earth-Moon system is not perfectly static. Motion continues to evolve as gravitational interactions redistribute energy. The same mechanism operates throughout the universe. Many moons in the solar system experience tidal interactions with their parent planets. Some migrate outward like Earth's moon, while others move inward depending on the details of their orbital and rotational dynamics. In the case of Mars, for example, the moon Phobos is slowly spiraling inward toward the planet rather than drifting away. Calculations suggest that Phobos may eventually break apart under tidal forces or collide with Mars tens of millions of years in the future. The Earth-Moon system therefore occupies a special balance where tidal interactions lead to orbital expansion rather than collapse. The outcome depends on the relative speeds of planetary rotation and orbital motion. Every year the Moon moves slightly farther away while Earth's rotation slows by a small fraction of a second over long timescales. These changes occur so gradually that human observers perceive the Moon as a constant presence in the sky. Yet the physics behind this motion reveals a dynamic relationship between Earth and its satellite. Gravity links the two bodies, while tidal interactions quietly reshape their motion across geological time. This continuing exchange of energy raises another fascinating aspect of the system. The same tidal forces that slowly push the Moon outward also shape the behavior of Earth's oceans and influence the stability of the Moon's rotation. Did the tides save the Moon from falling while also pushing it away? How can the slow rise and fall of Earth's oceans influence the motion of a world nearly 400,000 kilometers away? At first glance, tides appear to be a simple coastal phenomenon. Water moves toward shore, then retreats again several hours later. Yet behind this familiar pattern lies a subtle gravitational exchange that has been shaping the Earth-Moon system for billions of years. The same tides that lift the oceans by a few meters along coastlines are quietly altering the orbit of the Moon and the rotation of Earth itself. The gravitational attraction between Earth and the Moon produces two tidal bulges on our planet. One bulge forms on the side of Earth facing the Moon, where lunar gravity pulls the oceans slightly outward. A second bulge forms on the opposite side of Earth because the planet itself is pulled slightly toward the Moon, leaving the water behind. These twin bulges travel around the planet as Earth rotates. If Earth rotated slowly enough, the tidal bulges would remain aligned almost perfectly with the Moon. In reality, Earth completes one rotation in about 24 hours, while the Moon requires roughly 27 days to orbit our planet. Because Earth rotates far more rapidly, the ocean bulges are carried ahead of the Earth-Moon line. This small displacement has an important consequence. The bulges contain enormous masses of moving water, and their gravitational pull acts on the Moon. Because the bulges lie slightly ahead of the Moon's position, the pull includes a forward component along the Moon's orbital direction. That forward gravitational tug transfers a tiny amount of energy from Earth's rotation into the Moon's orbit. The Moon gains orbital energy and moves outward into a slightly larger path around Earth. Meanwhile, Earth's rotation loses energy and gradually slows. The mechanism behind this exchange is known as tidal friction. Ocean water does not slide across Earth's surface without resistance. As tidal currents move through ocean basins and across continental shelves, friction converts some of the motion into heat. This friction prevents the tidal bulges from aligning exactly with the Moon. The result is a constant gravitational interaction between the offset bulges and the Moon. Over millions of years, the accumulated effect alters the motion of both bodies. Astronomers have been able to measure this interaction with extraordinary precision using the laser ranging experiment that began during the Apollo era. Retroflector arrays placed on the Moon by Apollo 11, Apollo 14, and Apollo 15, astronauts allow laser pulses from Earth to bounce back toward their source. By measuring the round-trip travel time of the light, scientists determine the Earth-Moon distance with accuracy better than a few centimeters. These measurements show that the Moon's orbit expands by about 3.8 centimeters every year. That outward migration corresponds exactly to the energy transferred from Earth's rotation through tidal friction. Over long spans of time, the effect becomes significant. Geological records confirm that the relationship between Earth and the Moon has evolved dramatically since the Moon first formed. Evidence from ancient tidal deposits preserved in sedimentary rock layers suggests that Earth's stay was once much shorter than 24 hours. Several hundred million years ago, the planet completed a rotation in roughly 22 hours. Looking further back in time, researchers estimate that early Earth may have rotated once every 5 or 6 hours. At that time, the Moon orbited much closer to the planet. Strong tidal forces between the two bodies accelerated the transfer of rotational energy. Over billions of years, the Moon moved gradually outward while Earth's spin slowed. The distance between the two worlds increased from perhaps 100,000 kilometers in the distant past to the current average distance of about 384,000 kilometers. The scientific study of tides began long before spacecraft visited the Moon. In the 17th century, Isaac Newton recognized that the Moon's gravitational pull must influence Earth's oceans. Newton's explanation connected the daily rise and fall of tides to the same universal law of gravity that governs the motion of planets. Later, researchers expanded on this insight by examining how tidal friction influences long-term planetary motion. The British physicist George Howard Darwin, son of Charles Darwin, analyzed the Earth-Moon system in the 19th century and proposed that tidal interactions could gradually change orbital distances. Modern observations have confirmed the essential elements of that prediction. Measurements from satellites, oceanographic studies, and lunar laser ranging experiments all support the conclusion that tidal friction transfers energy from Earth's rotation to the Moon's orbit. The effect is small in human timescales, but powerful over geological history. Each year, Earth's day becomes slightly longer as rotational energy continues to dissipate. Carl Sagan once emphasized the importance of recognizing the dynamic nature of planetary systems. He wrote, "The universe is not static, it is evolving." The Earth-Moon pair offers a clear demonstration of that principle. The familiar motion of tides along coastlines reflects a slow but continuous evolution of the entire system. Ocean tides reshape shorelines and ecosystems on Earth. At the same time, they influence the orbit of a celestial body nearly 400,000 kilometers away. This interaction links everyday experiences on Earth with the mechanics of celestial motion. The Moon also responds to tidal forces raised by Earth. Just as Earth's oceans are stretched by lunar gravity, Earth's gravity once raised tidal bulges in the Moon itself. Those bulges played a role in slowing the Moon's rotation until it became tidally locked. Because of that process, the same hemisphere of the Moon remains directed toward Earth today. The near side and far side of the Moon therefore experience very different observational histories. Humans observed the near side for thousands of years before spacecraft revealed the far side during the 20th century. The tidal interaction between Earth and the Moon, therefore, produces two simultaneous effects. It gradually slows Earth's rotation while expanding the Moon's orbit. At the same time, it stabilizes the Moon's rotation so that one face always points toward Earth. Despite these changes, the Earth-Moon system remains gravitationally bound. The outward drift of the Moon occurs extremely slowly compared with the size of the orbit itself. At the present rate, it would take more than 100 million years for the distance to increase by only 4,000 kilometers. This gradual evolution shows that the Earth-Moon system is not fixed, but continually adjusting through gravitational interactions. Ocean tides represent the visible surface of a deeper physical exchange occurring between two worlds. Each tidal cycle carries a tiny fraction of Earth's rotational energy into the Moon's orbit. Over billions of years, this transfer has reshaped both the length of Earth's day and the distance of the Moon. The relationship between these processes reveals how even familiar natural phenomena connect directly with orbital mechanics. The rise and fall of the oceans reflects gravitational forces acting across hundreds of thousands of kilometers. Yet, the modern appearance of the Moon does not fully reveal the dramatic history of the Earth-Moon system. Geological evidence suggests that the Moon once orbited much closer to Earth and looked very different from the world we see today. Was the Moon born too close to Earth to look anything like it does now? What if the Moon that hangs above Earth tonight once filled half the sky and orbited our planet at a distance so small that a single day on Earth lasted only a few hours? The calm motion we see today hides a violent beginning. Modern evidence from lunar samples, orbital measurements, and planetary simulations reveals that the Moon likely formed during a catastrophic collision early in the history of the solar system, when Earth was still young and the architecture of the planetary system had not yet stabilized. To understand this origin story, scientists begin with a remarkable collection of material brought back from the Moon during the Apollo missions. Between 1969 and 1972, astronauts from the National Aeronautics and Space Administration returned to Earth with a total of 382 kilograms of lunar rock and soil. These samples came from 6 different landing sites scattered across the lunar surface. Laboratories around the world began analyzing these rocks almost immediately. Geologists examined their mineral composition, their age, and the chemical signatures preserved inside them. The results produced an unexpected discovery. The Moon's material closely resembles Earth's mantle rather than the composition of independent planetary bodies found elsewhere in the solar system. This similarity suggested that the Moon did not form far away and later become captured by Earth's gravity. Instead, the evidence pointed toward a shared origin. The Moon must have formed from material that once belonged to Earth itself. The leading explanation that emerged from this evidence is known as the giant impact scenario. According to this model, a young Earth experienced a collision with a planetary body, roughly the size of Mars. That object is often referred to by researchers as Theia. Computer simulations developed during the late 20th century began exploring what such a collision would produce. When 2 planetary bodies of that scale collide at high velocity, enormous amounts of rock and metal are ejected into space. Some of that debris escapes entirely, but a significant fraction remains gravitationally bound to the larger body. In the case of Earth, the simulations suggest that a disk of vaporized and molten material formed around the planet after the impact. Within this disk, fragments of debris gradually collided and merged. Over time, these fragments assembled into a single large object that became the Moon. The timescale for this process appears surprisingly short in planetary terms. Many models indicate that the Moon may have formed within a few thousand years after the initial collision. Once the debris disk condensed into a single body, the newly formed Moon entered orbit around Earth. At that early stage, the Moon likely orbited far closer to Earth than it does today. Some models estimate the initial distance to have been less than 30,000 kilometers. By comparison, the Moon's present average distance is about 384,000 kilometers. At such a close distance, the appearance of the Moon in Earth's sky would have been dramatically different. Its apparent size could have been more than 10 times larger than what we see today. Tidal forces between the two bodies would have been far stronger as well. Evidence from geological records suggests that Earth rotated much faster during this early period. Some models indicate that a single rotation of Earth may have taken only 5 or 6 hours shortly after the Moon formed. The enormous tidal forces generated by the close Moon would have raised massive ocean tides and deformed the solid surface of the young planet. Over millions and then billions of years, tidal interactions gradually changed the configuration of the Earth-Moon system. Energy transferred from Earth's rotation into the Moon's orbit pushed the Moon outward. At the same time, Earth's rotation slowed. The present configuration we observe today, therefore, represents only one moment in a long evolutionary process. The Moon that now appears calm and distant once orbited much closer and moved across the sky far more quickly. Lunar rocks brought back during the Apollo missions provide additional clues about this early history. Radiometric dating techniques allow scientists to determine the age of lunar samples by measuring the decay of radioactive elements within the minerals. These measurements consistently show that most lunar rocks formed around 4,400,000,000 years ago. This age places the formation of the Moon roughly 60 million years after the beginning of the solar system. The solar system itself formed about 4,560,000,000 years ago, when a collapsing cloud of gas and dust created the Sun and the first planetary building blocks. During those early tens of millions of years, collisions between planetary embryos were common. Large bodies frequently collided and merged as the planets grew to their present sizes. The giant impact that formed the Moon appears to have been one of the final major collisions in Earth's formation. Further evidence supporting the giant impact scenario comes from isotopic analysis of lunar material. Oxygen isotopes found in lunar rocks match those found in Earth's mantle almost perfectly. Such similarity would be extremely unlikely if the Moon formed elsewhere in the solar system and later became captured. The internal structure of the Moon also supports this origin. Seismic experiments conducted during the Apollo missions detected moonquakes and revealed information about the Moon's interior layers. These measurements show that the Moon possesses a relatively small metallic core compared with Earth. This structure aligns well with the giant impact model. The collision would have ejected material primarily from the outer layers of Earth and the impacting body, rather than from their metallic cores. As a result, the Moon formed mostly from mantle material. Modern planetary simulations continue refining this picture. Advanced computer models run by researchers at institutions, including the National Aeronautics and Space Administration and the European Space Agency, simulate the physics of planetary collisions with increasing realism. These models show that an impact between bodies of appropriate size and velocity can reproduce the observed mass, orbit, and composition of the Moon. Carl Sagan once described the importance of studying planetary origins in a way that resonates strongly with this story. He wrote, "If you wish to make an apple pie from scratch, you must first invent the universe." The formation of the Moon reminds us that even familiar celestial objects emerged from complex cosmic processes operating during the earliest chapters of the solar system. The Moon we see today, therefore, represents the outcome of billions of years of gravitational evolution following an extraordinary beginning. A collision reshaped the young Earth, debris formed a new world, and tidal interactions slowly carried that world outward into the orbit we observe now. Yet, the deeper significance of this history extends beyond the Moon itself. Once the origin of lunar motion becomes clear, the same physical principles appear throughout the universe in the orbits of planets, stars, and even matter circling black holes. Is the real mystery not why the Moon doesn't fall, but why orbit exists at all? If gravity constantly pulls the Moon toward Earth, why does the same rule allow planets to circle the Sun, satellites to circle Earth, and stars to circle one another for billions of years without collapsing inward? The answer begins with a realization that quietly reshapes the way we look at the night sky. The Moon remains above us, not because gravity fails, but because motion and gravity are balanced with remarkable precision. The Moon is falling toward Earth every second. Yet while it falls, it also moves sideways fast enough that the surface of Earth curves away beneath it. The result is an endless fall that never reaches the ground. This idea was first clarified during the 17th century by Isaac Newton. Newton imagined a thought experiment involving a cannon placed on a very tall mountain. If the cannon fires a ball gently, the ball falls to Earth, a short distance away. If the cannon fires faster, the ball travels farther before hitting the ground. But if the ball leaves the cannon with exactly the right sideways speed, something extraordinary happens. The ball keeps falling toward Earth, yet Earth's curved surface drops away beneath it at the same rate. The cannonball never lands. It becomes an orbiting satellite. What Newton described in this simple mental picture turns out to govern the motion of nearly everything in the universe. Orbit is not a special condition reserved for the Moon. Orbit is the natural outcome whenever gravity pulls inward while motion carries an object sideways. In the case of the Moon, the sideways speed is about 1 kilometer per second relative to Earth. That speed is precisely tuned to Earth's gravitational pull at a distance of roughly 384,000 kilometers. If the Moon moved significantly slower, gravity would draw it inward and its orbit would shrink. If the Moon moved significantly faster, it could escape Earth's gravitational hold entirely. The balance between gravity and motion appears again throughout the solar system. Earth itself follows the same principle as it travels around the Sun. Our planet moves along its orbit at roughly 30 kilometers per second. At that speed, the Sun's gravitational pull bends Earth's path into a nearly circular orbit rather than allowing the planet to drift away into interstellar space. This balance explains why planets do not fall directly into the Sun. Each planet carries sideways motion inherited from the early formation of the solar system. That motion began when the cloud of gas and dust that formed the Sun started rotating. As the cloud collapsed under gravity, conservation of motion caused the rotation to increase. The remaining material flattened into a rotating disk surrounding the young Sunday. Within this disk, small particles collided and gradually formed planetesimals, then protoplanets, and eventually the planets we recognize today. Because the disk was already rotating, every planet formed with substantial sideways motion. That inherited motion is what allows Earth, Mars, Jupiter, and the other planets to remain in orbit. Gravity constantly pulls them inward toward the Sun, while their sideways motion continuously carries them forward. The same pattern extends far beyond our solar system. Astronomers observing distant stars frequently discover binary star systems in which two stars orbit one another. In these systems, gravity pulls both stars toward their shared center of mass, while their sideways motion keeps them circling rather than colliding. Even entire galaxies follow this principle. Billions of stars orbit the center of the Milky Way galaxy. Our own Sun completes one orbit around the galactic center approximately every 230 million years. Closer to Earth, orbit defines the environment of modern technology as well. Thousands of artificial satellites circle Earth at various altitudes. Communications satellites, weather satellites, and navigation satellites all remain above the planet because they travel sideways fast enough to remain in continuous freefall. The International Space Station offers a particularly clear example. This spacecraft orbits Earth at a speed of roughly 7.7 kilometers per second. At that speed, it circles the planet about once every 90 minutes. Astronauts aboard the station experience weightlessness, not because gravity disappears, but because the station and everything inside it are falling together toward Earth. Since the station keeps missing the ground as it moves forward, the fall never ends. Modern space exploration relies heavily on the precise understanding of orbital motion. Space agencies such as the National Aeronautics and Space Administration and the European Space Agency calculate spacecraft trajectories using the same gravitational principles first described centuries ago. When a spacecraft travels to the Moon or to another planet, engineers carefully adjust its speed so that gravity bends its path exactly as intended. A small change in velocity can transform a spacecraft's path from a circular orbit into an elliptical orbit, or even into a trajectory that escapes a planet's gravity entirely. This delicate balance between gravity and motion also appears in extreme environments near black holes. Gas and dust falling toward a black hole rarely plunge directly inward. Instead, the material forms a rotating disk known as an accretion disk. Within this disk, particles orbit the black hole at enormous speeds. Gravity pulls them inward while their motion carries them around the black hole in rapidly spinning paths. Observations from telescopes such as the Event Horizon Telescope have revealed glowing rings of matter orbiting near black holes in distant galaxies. These observations confirm that the same gravitational principles apply across vastly different scales. From the Moon circling Earth to stars orbiting supermassive black holes, the universe repeatedly produces the same dynamic pattern. Carl Sagan once summarized the significance of such universal laws with a statement that continues to guide scientific exploration. He wrote, "Somewhere, something incredible is waiting to be known." The simple idea that objects remain in orbit because they are constantly falling while moving sideways has opened the door to understanding a wide range of cosmic phenomena. When the concept becomes clear, the night sky begins to look different. The Moon is not suspended in place. The planets are not fixed along invisible tracks. Everything in the sky is moving, responding to gravity and motion in a continuous interplay that shapes the structure of the universe. The Earth-Moon system, that began with a violent impact billions of years ago, now demonstrates a stable example of orbital balance. Tidal interactions slowly change the distance between the two worlds. Earth's rotation gradually slows. Yet the overall pattern of orbital motion remains remarkably stable across immense spans of time. Understanding orbit therefore answers a question that appears simple at first glance, but leads into the foundations of celestial mechanics. the Moon does not remain above Earth because gravity is weak. It remains above Earth because motion and gravity operate together in a precise relationship that nature repeats throughout the cosmos. And as this exploration comes to its final moments, there is a quiet appreciation for the patience of everyone who has followed this journey from the familiar sight of the Moon to the deeper mechanics that keep it moving through space. The curiosity and attention that you bring to these questions are what allow scientific stories like this one to continue. Thank you for spending this time exploring the science behind the motion of the Moon and the wider universe. If this journey has helped the night sky feel a little clearer and a little more understandable, then the time shared here has already served its purpose. Wherever you may be listening tonight, may the steady motion of the Moon above Earth offer a quiet reminder that the universe is built from motion, balance, and time. Good night, and rest well.